Okay, welcome here to lecture. We're continuing on here talking about equilibrium. Um, so last time we talked about or started talking about equilibrium. Remember that equilibrium is again the idea when a chemical reaction basically reaches a point where the forward reaction will equal really the reverse reaction. And what we're talking about is in terms of equal is again not necessarily that they have the same concentrations or same pressures or things of that nature, but what we're talking about is actually the rate. So as we talked about last time, there's really a specific type of reaction that we deal with in chemical equilibrium, and those are those reversible reactions. So as we talked about last time, it's those reactions that basically head in sort of both directions. We have these reversible arrows here to sort of indicate that. And what we mean when we get something that sort of reaches chemical equilibrium is the idea that the rate of the forward reaction, and that would be going from reactants to products, would equal basically the rate of the reverse reaction, which would be the opposite there, obviously, going from products back to reactants. So, what that means is essentially you have reactions heading in opposite directions, pretty much equal to each other in terms of their rate. And what that ends up doing is, as we talked about last time, is it essentially will lock into place sort of everybody where they're at. And again, it doesn't mean that they have the exact same concentrations. In my example up here, it doesn't mean that A and B and C and D, when it reaches equilibrium, they will all be equal in terms of what they have on their concentrations or pressures or things of that nature. But it just means just as quick as it kind of goes to the right hand side of that reaction, it comes back the other way just as quickly. And again, we get this sort of locking in terms of concentrations at that point. Um, we talked about a relationship, obviously, that's known as the equilibrium constant, which is like the big topic in this class, and that is capital K, not to be confused with lowercase k, which was our rate constant, but capital K here, which again is basically our products, the concentration of our products divided by the concentration of our reactants. And when we do sort of concentrations, that's what's referred to as Kc. In this case, C obviously being for concentration. And we do take the coefficients into account. So if there was a coefficient here, say a 2, when we would do that part, it would be a squared because of that coefficient when we put that in there. So we do take the coefficients into account when we do that, and it gives us a relationship that is always constant. And as we'll talk about in this chapter, really the only thing that can sort of affect the value of the equilibrium constant is temperature. But if you sort of start the reaction with different amounts of reactants, for example, it will always come to rest sort of at equilibrium in the same proportion of products to reactants. So you'll get the same K value as long as you don't change the temperature. So if you did a bunch of different reactions, say at 25 degrees Celsius, and you started with the same overall reaction, but a bunch of different sort of starting amounts in a particular reaction of reactants or products, whatever it may be, it will come to rest at the same sort of equilibrium proportion of products to reactants every time. And that should be a constant value that you get. Again, though, if you do change the temperature, say from 25 degrees to 50 degrees Celsius, the value of K will actually change between those two temperatures. But once you get it to say 50 degrees Celsius, it will remain, constant at that temperature again, as long as you don't change the temperature. So we have that sort of relationship of products to reactants. Remember, it is just a number. So there's usually no units involved with K. We just see a number, and remember that number will tell us some pieces of information. It tells us, if it's a large value of K, what that really means is, again, if we just think about this mathematically, a large value of K can really only be achieved there by having a lot of products, right? So larger number on top, smaller number on the bottom gives us a larger value of K. And that would be a situation which we would expect mainly products to occur. we have a small value of K, that means kind of the opposite. It means here we would have more reactants when we're dividing. So smaller number on top divided by a larger number on the bottom gives us a smaller number for K. And what that tells us is we will probably mainly have reactants when we reach equilibrium. Now, what is a large number and small number? As we talked about last time, a large number or a small number, it all revolves around 1. So kind of anything above 1 is considered sort of a large value of K. Anything less than 1 is considered a small value of K. And again, we can make that sort of determination. We also saw that in addition to sort of the KC in our ever-growing list of Ks, and we'll have a lot of them as we go through the semester here, we can also do like a KP, which is like the partial pressures of the products divided by the partial pressures of the reactants. And again, it works the same way. You would also, again, if you had that coefficient, instead of, and that was a gas, it would be the partial pressure squared of A when you would put it in there. So here, you know, typically when we talk about pressures, we talk about equilibrium, and especially later when we talk about solving equilibrium problems, a lot of times we want to deal with pressures in terms of atmospheres. It's sort of the standard unit. And a lot of times it's a good idea to convert things into atmospheres to do the calculations, and especially later on in this chapter, we'll talk about some calculations, but kind of important to have it in atmospheres, even if perhaps it asks you for a different unit of pressure or something like that. And, you know, it gives you a different unit. It's a good idea to turn it into atmospheres, do the conversion, and then sort of convert it back to whatever units you're looking for. And to sort of tie those two together, we oftentimes saw a relationship between those two, that the, what was that there? The Kp is equal to the Kc, RT delta N, this being our equilibrium constant for pressure, this guy, our equilibrium constant for concentration, our gas constant, just like using the ideal gas law, 0.08206 or 21, temperatures in Kelvin. And this guy, as we talked about last time, really important, which is the change of moles. So again, that is your moles of your product minus the moles of your reactant, and those are for gas molecules. And also important, like we talked about last time, that if you do get a negative in that situation, you should keep the negative, because mathematically it is sort of a different math problem if you have a negative number for that or you don't. So again, you know, especially for this part of it here, the Kp is equal to the Kc RT delta N. Again, it's very common. People just take the difference of the gas molecules, not worrying about the sign. But again, mathematically here, you want to make sure you worry about the sign. Usually, in a lot of cases, the Kp and Kc are not the same value. It potentially could happen, but usually they're not the same value in terms of numerical value. But they do really tell you sort of the same information. You know, again, if you have a large Kp value, you would expect mainly products. Small Kp value, you expect mainly reactants. Is there any questions on any of that stuff there that we talked about last time? Okay. So where we left off was sort of here, I think, just talk a little bit about heterogeneous equilibrium. Heterogeneous equilibrium is basically when we have different states. So just like, you know, when we talk about heterogeneous mixtures, things are in different states, things look different. Same thing here when we have heterogeneous equilibrium. What we're talking about is pretty much everybody's in different states, or a number of different states along the way. So if we look at something like calcium carbonate that breaks apart into calcium oxide and carbon dioxide, we have some solids, we have some gases. So if we just take the approach of writing our equilibrium expression like we did before, where we take products over reactants, we will end up with this sort of expression. The problem with sort of this expression is we have a couple of solids here. We have this guy's a solid, this guy's a solid. And to be honest with you, the solid is pretty much not participating. You can kind of think about it as almost like sitting on the bottom there, not really doing much at any particular point. They do remain relatively constant, which means if we were to write our equilibrium expression, we actually would want to sort of not include those in there. And basically what that will give us is the actual equilibrium constant for this guy here, which would be the Kc is equal to the concentration of CO2. Now we could also write a Kp for that as well. And the Kp for that would also be the same situation here, since this guy is a gas. We could write that the Kp is equal to the partial pressure of CO2. Sorry about that, I got a little out of control. And this I'm just going to kind of cross out. Don't worry about this here. So this is just showing that it is constant, and that's why there's a prime here. It's to show these two are constant. So when we multiply those two, then we get really the Kc value, or the Kc expression that we're looking at, which is basically just the CO2. So ultimately what we end up with here, as we talked about, I think as well last time, is that the concentration of solids and pure liquids, they're typically not included at all in an equilibrium sort of calculation or expression. So basically, if you see anything with an S, if you see anything with an L, you pretty much should not put it into your expression. You pretty much should just kind of ignore it in that situation. So as we talked about last time, what that really means is pretty much when you're doing your K expression, what goes in is pretty much at this point aqueous guys and gases go in. Those are okay. In terms of K, liquids and solids, not okay. Yeah, you leave out basically. Any questions on that? Okay. So it's just this picture kind of showing you, again, for the most part, not really participating with the gases here, kind of remaining on the bottom here are solids. So again, we don't really necessarily worry too much about it in terms of the equilibrium. And again, if we look at sort of this picture here, especially in this sort of case, we're measuring the pressure, as you can see here. And the pressure is sort of unaffected, if you will, by the solid here sort of even maybe changing. It will change. So if you have a sort of a system at equilibrium, you could make more solid on one side or the other, but not really participating there with the gases, because they are definitely moving around and really participating with each other, and that's really going to have a major effect on sort of the pressure of that system, and that's why we look into those guys. So if you think about sort of the two things that so if you think about the two things that we basically don't put into our equilibrium expression, and that is our liquids and solids versus our aqueous and gases. Major difference between these two guys really is, if you think about sort of a situation. So if we have something that's aqueous, right? Those are basically ions. Those are basically guys kind of floating around, ready to go, to react, to interact with each other. So they do have obviously an effect. Obviously here, gas molecules are also like moving around, flying around. They're interacting with each other a lot of the time. Obviously, big effect there on pressure. So, we really, in terms of equilibrium, focus on those guys that are, I don't want to say really active, or really there and kind of constantly interacting with each other and really having an effect on it. Again, just the byproduct of that is, we might make some of these things. Remember, in order for the solid to maybe interact, it may have to sort of decompose to a gas, or maybe get into sort of aqueous. And at that point, it's going to be one of these guys, aqueous or gas, sort of interacting at that point. The solid itself, sort of sitting there. If you want to think about it, kind of like a brick, you throw a brick into some water, it's probably just going to kind of float to the bottom. At some point, a rock or a mud sort of rock, if you will, at some point, the rock may, or the mud clot there may start to sort of dissolve. And at that point, when it dissolves, it may be able to interact with things. But, in sort of its solid form, it's just kind of sitting there, until maybe it starts to deteriorate or something like that. Any questions on that? Okay. So why don't you give this one a go here, see what you come up with. We have the following reaction here. We want to calculate the Kp and the Kc for this reaction. The partial pressures of both gases are 0.265, it looks like. So see what you come up with. Again, looking for two answers, Kp and Kc here. So take a few minutes here, see what you come up with. Then we'll talk about it and see how you did. Given some pressures here, which is obviously going to mean probably Kp is the proper place to sort of start here. To do that, we would want to write our Kp expression. Our Kp expression, again, going to be our products over reactants, and it's going to be the partial pressure in this case of NH3, again, coefficient 1, so we don't have to do any type of squaring or anything like that, times the partial pressure of H2S, same deal, kind of a coefficient of 1 there. And now for our reactant side, this guy is a solid, which means he should not be included. So this should be the Kp expression. Since the pressure of both gases each are 0.265, we pretty much could just plug that in. So 0.265 times 0.265, going to get us something like 0.0702 in that particular case. And that would be the value for our Kp. Any questions up to that point there? Now, once we do have the Kp, we can then figure out the Kc value. And again, we would want to use that equation that we saw previously, which is that the Kp is equal to the Kc. RT delta N, our temperature was already given to us in Kelvin. So if not, remember just a 273 addition to Celsius if it's not given to you, obviously in Kelvin. That means we do want to figure out delta N. So remember that delta N here is the moles of the product minus the moles of the reactants. On the product side, I got 1 gas molecule there, 2 gas molecules there. On the reactant side, again, this being a solid means we got nothing there. So in this case, our delta N would equal 2. At that point, we have 0.0702 for our Kp. Our Kc times our R value times our temperature, which was already in Kelvin. And again, we're going to basically square that whole thing. Kind of cleaning up the right-hand side there. We'll take 0.08206 times the 295. We'll also do a little squaring of that. That's going to give us 0.0702 is equal to Kc times like 586.0127, not so much rounding. Then again, obviously divide that to the other side there, and that will get me my Kc value, and that would end up being, in this case, looks like we'll call it a Kc that equals something like 1.20 times 10 to, how many zeros there? 1, 2, 3, 4, minus 4 in that particular case. Question on any part of that calculation where we got any of the numbers or anything I can answer for you. So when we do have this type of situation, we want to kind of think about which one it makes sense to start with. And again, using this formula here allows us to go from one to the other. Here, remember as well, it kind of does tell us the same thing. We see that the Kp and the Kc are not numerically equal to each other, but they both would be considered a small value of K. And because they both would be considered a small value of K, what that means is when we do reach equilibrium, we would mainly expect to have reactants present at that point. Question on Kp, Kc, how to calculate them. Obviously, you need to know how to do that given the information provided to you. Okay, then another thing that's important in terms of equilibrium is, sometimes we need to kind of manipulate equations, these reversible reactions, to get a specific equation we're looking for. So this is kind of like perhaps what you learned when you did Hess's law. If you remember what Hess's law was, when you add up all those kind of individual reactions, it gives you like an overall reaction. And sometimes you need to do that with sort of equilibrium type of reactions. Sometimes you need a reversed reaction. Sometimes you need to add a couple of reactions together. And again, that's because, as you're probably aware of, not all reactions really do take place sort of in one step all the way across. So again, here what we see is, maybe it's a two-step process here where the first step is A plus B goes to C plus D. and then C plus D react to make E plus F. So if we were to add these together, which is essentially what they did, anything on opposite sides of the arrow will cancel out or reduce, and what we're left is this overall reaction. And if we wanted that overall reaction sort of K value, how could we get it? Well, this guy right here is the equilibrium expression for the first reaction. This guy here is the equilibrium expression for the second reaction. And essentially speaking, if we multiply these two guys together, C's would cancel, D's would cancel. And what that would leave you when it all comes together is the actual equilibrium constant for the overall equation here. So one very common way of sort of manipulating equations or reactions is if you need to add a reaction together or multiple reactions together, what you essentially do with the K value is multiply it. So again, that's a little bit different than a lot of people would think. A lot of people would think I'm adding the reactions together, I should just add the K values. That kind of makes sense, but you would actually be wrong in this case. As you can see, mathematically speaking, what's really happening is you're multiplying the K values. So if you add two reactions together, you multiply the K values for each reaction, and that will give you the K value for the overall reaction. Again, if you're adding 3, 4 reactions together to make an overall reaction, again, you will continue to sort of multiply the K values. So that's, again, an important distinction. Sometimes people do get confused on that. They think, well, it does sort of logically make sense in that sort of thought process, like, hey, I'm adding these things, so I probably should just add, the K values. But you actually multiply the K values. Another sort of way that we sometimes manipulate sort of these reactions is maybe we don't need the reaction the way it's written, but maybe we need sort of the reverse of that reaction. So maybe we need the reactants on the product side, products on the reactant side. So sometimes we need to sort of reverse the reaction. And when we reverse a reaction, like we see here in this particular example, we get our products over reactants, and in this particular equation, the K value is 4.63 times 10 to the minus 3. Number is really not important right now. But basically, as we go from the reaction on the left to the reaction on the right, essentially the only thing we did is basically reverse it. And again here, what ends up happening is when we do our products over reactants, our denominator became our numerator became our denominator here. And basically what that means is we basically reversed it or inversed it, if you will. We took 1 over the K value would be how we would get to the K value for this equation up on top. So if there's a necessary need for you to reverse a particular reaction, what you would do is actually take 1 over the K value, and that would get you the K value for the new reaction. It's important to remember that when we talk about K values, for example, if I said this reaction has a K value of 4.63 times 10 to the minus 3, I am specifically referring to this reaction where this is the reactants, this guy is the products at a specific temperature. This number would not be the K value for this reaction the way it's written. It would actually be this number here, obviously, is the K value. So when we sort of specify a K value for a reaction, we're specifying that number for a couple of things. The first thing is we're saying it is for that reaction exactly how it's written. Whatever's on the reactant side, whatever's on the product side, that is where we get our K value from. The second thing is we're saying basically that it is also for a specific temperature, whatever that temperature may be. Any question on those two sort of manipulations of those reactions? Now, there's also a couple of other things that do occur as well. And again, kind of similar to maybe some things that you had to do when you dealt with, say, Hess's law and kind of using those different equations. If we had, say, a reaction such as this, and it had a K value, which would basically be the concentration of C times concentration of D divided by the concentration of A and B. Now, let's say I'm looking at this, but I don't need just one A or something. I need two. So that would require me to multiply this reaction by a common number all the way across, and that would be 2A plus 2B gives me 2C plus 2D. What does that do to our equilibrium expression? Well, we end up with then C squared, D squared divided by A squared and B squared. So what actually happened to our equilibrium sort of constant as we went from here to here? Well, I multiplied by 2, and I essentially needed to square everybody. So the K value got basically squared in that case as we went that way. If I multiplied by 3, it would then be cubed. If I multiply by 4, you would take it to the 4th power. So if you need to multiply by a common number, what ends up happening is you take the K value basically to that common number. So again, like we did on the bottom there, we squared it because of we multiply by 2, so we basically squared it. If we multiply by 3, we would cube it. Now, the same thing can be thought of, though you may need to divide by a common number. And let's just say we needed one of everything, so we'll go backwards, going this way. So let's say we want to go in that direction. We basically divided by 2, which means in terms of our K value would actually be going in this direction. And what happens as we go from the K value on the bottom to the K value on the top in that direction? We're actually taking the square root of it. And if you take the square root of those guys, so basically our K went from there to a square root of K in that case. If we divided by 3, you would then take the cube root of it. If you divided by 4, the 4th root, and so forth. So if we divide a reaction by a common number, you basically take the K value and take the square root of that number, basically. So you basically do that again. If it was a 2, you would take the square root. If it was 3, you would take the cube root, and so forth. So those are the common sort of ways that we manipulate some of these equations. Again, this would be a situation where you're given, a bunch of individual reactions, and you're trying to build out sort of an overall reaction. Any questions on that there? Okay. So let's just see. Let's say we had something like let's say we wanted 2A plus 2B went to E plus F, for example. So let's say we have those guys there, the A plus B. Let's see if this will work here. Goes to C plus D. And let's say the K is equal to 20. Just work one out real quick here, maybe, or try to figure out one here real quick. Let's see here. Let's just do it like that. Perfect. And actually, let me do it this way here real quick. And do this. All right. So let's go. Okay, so let's say given the K values for these two reactions here, you want to basically kind of build this reaction here. And you want to basically figure out what the K value is. So take a minute or two and see what you come up with. I'm going to do it too. I just made it up, so we'll hope for the best here. So take a minute and see what you come up with. Again, you need to manipulate those upper equations to get to the below one. And again, we'll hope it works. Um, so again, probably you could take a sort of the same approach as maybe you used when you did sort of Hess's law. The simple approach is always probably the best. Here, we just want to kind of see where everybody's at in terms of sides. So here I see A's are on the reactant side, but the guys over here with A's are on the product side. So I do know that I need to reverse that reaction. So I got to reverse it and make our A and B come to our reactant side, our C and D go to our product side. Now, because I just reversed it, remember when we reverse a reaction, we're going to take not the negative of it, which is a very common thing people want to do. We're going to take 1 over the K value, which means at this point, based on my sort of manipulation of the top equation, I have now basically took 1 over 20. Any questions on that so far? In addition, now that I got A and B on the right side, or the correct side, I guess a better way of putting that in this case, I also want to think about how much of those guys I need. In this case, I actually need 2 of them, which means in addition, I now need to multiply this top guy by a common number of 2 all the way across. Remember, when I multiply by 2, I'm not going to multiply the K value, but I'm actually going to square the K value. So again, it's important to kind of keep track of everything you're doing to the K values so that you hope you'll get the right answer there at the end. Now let's take a look at the other side. I got E and F on the product side, which I do over here as well. But again, here I don't need 1 of them, but I need 2. So I need to take that top or that bottom reaction there. And I'm going to take the K value here. First, I'm going to multiply everybody by 2. And in terms of the K value, what that means again is I'm going to take that K value and square it, which means I would take 10 squared in this case. At this point, we want to make sure, obviously, we end up with sort of the right reaction that we were looking for. That means that when we add them together, the 2 C's would cancel, the 2 D's would cancel. That leaves us with 2A plus 2B, going to go to 2E plus 2F. That is good. That is what we were looking for here. Now, again, an important part here is we are not going to add those numbers, but we're going to multiply them. So when we get a couple of numbers here, that's going to be 1 divided by 20, and then we're going to square it, and that will get us something like 0.0025. We're going to obviously take 10 squared in that case, going to give us 100. And again, what we're going to do then is for the K value for this guy is multiply those 2 together. Again, not adding them, we're going to multiply them together, and that would get us, looks like 0.25. I guess I didn't do too bad in my making up of numbers here. Any questions on that manipulation? Again, this would be a similar type of problem where you're given individual reactions with their K values, then you sort of has to manipulate them, stuff like that. So you want to keep in mind how the equilibrium constants are sort of manipulated or changed as you multiply by a common number, divide by a common number, reverse the reaction. Again, it's a very common mistake that students make, that they kind of fall back on that Hess's law type situation. When they reverse a reaction, instead of doing 1 over it, they do like the negative. Instead of at the end there multiplying the K values, they add them and stuff like that. So those are very, very common mistakes that people make when they're sort of doing these type of problems. Any questions on that? Okay, then we'll continue on. This is sort of some of the stuff, or a lot of the stuff that we talked about. So just to reiterate, when we're talking about concentrations, usually we're talking about molarity with our equilibrium. As I mentioned before, if you're doing something with pressures, again, it's really atmospheres is where it should be. So you might have to do that 760 torr is equal to 760 millimeters of mercury is equal to 1 atmosphere. Remember, there's other units as well of pressure, things like bar, things like pascals, kilopascals. But, you know, probably most of the time, you'll probably be given it in atmospheres if it is pressure, but other than that, maybe torr or millimeters of mercury, again, still very common units that are given. As we talked about, really, again, no solids or liquids. So anything with the S or L sort of designation there does not end up at all ever in a equilibrium expression. Again, really just our aqueous and our gas molecules there is what ends up. One of the nice things, I guess, about the K value is it is just a number. So again, no units needed for it. And as we've been talking about here just a second ago, when we talk about sort of the actual value for K for a particular reaction, we are talking about exactly how it's written and at the specific temperature. So again, the temperature is sort of the one thing that will basically change the numerical value, if you will, of the equilibrium constant. When we sort of add reactions together, like we were just doing there, we want to multiply the K values together. And again, some other sort of manipulations like we talked about. If we need to multiply by a common number, we take it to the common number. If we need to divide by a common number, we take kind of the root of that number, the K value to the root of that number as well. So those, again, are the common types of manipulations that we do with these equations. Now, again, an important thing to remember, and it's really sort of a hard concept for students to sort of grasp, is that idea that we were talking about, that you will always end up with the same K value at a given temperature, regardless of the amounts of reactants or products that are initially present. So, if you again started with, some A and some B in a reaction at 25 degrees Celsius, that reaction should come to equilibrium with a certain number in terms of the value of it. If you ended up starting with, some A, some B, maybe a little bit of C, it also should come to rest at the same proportion. So regardless of sort of your starting amounts, and again, sometimes people think, well, I started in this reaction with like 4 of this guy and 4 of this guy, but then the next time I did the experiment, I did like 2 of this guy and 3 of this guy. How come the Ks are still the same? And again, it's just because of the rate of that forward reaction, that reverse reaction will always come equal to each other. And what ends up happening is, regardless of sort of the numbers, the proportion of products to reactants end up being the same number. So a sort of simple way to think about that is, when we think about, say, the number 2, for example, there's a multiple ways you could get to 2. I could do 4 over 2, which would equal 2, right? I could do 8 divided by 4, which equals 2, right? So there's multiple ways. I'll keep going, maybe one more time, maybe not. But there's multiple ways you could kind of get to the number of 2, right? And even though you have different amounts at sort of equilibrium, but sort of the ratio that happens gets you to sort of the same conclusion. And that's what happens with sort of equilibrium reactions. Again, whatever you're starting with, and again, you could be starting with some here and here only, maybe some here, maybe all everywhere. But, when they hit that ratio of the products to reactants and that rate at which they sort of equal each other, of the forward reaction equaling the rate of the reverse reaction, again, this sort of proportion, if you will, ends up like this. You always sort of end up with the same sort of proportion of products to reactants, and that's why we end up with sort of the same value for K. Now, again, as we talked about, there are many equilibrium positions, and that's what it means by that there's many equilibrium positions, but only one value of K for a particular reaction. And again, as long as you maintain the temperature, that K value should technically be a constant value. Any questions on that? Okay. Then let's talk about another letter, actually. It's a little bit different of a letter, and that's actually Q. And Q is what is referred to as the reaction quotient. And the reaction quotient is sort of used for a situation where, in this sort of application, we're not really sure we're at equilibrium. And we could use the value of K to help us determine if we've actually hit equilibrium or not. How do you calculate Q? Well, Q is calculated the exact same way as K, which means if you wanted to sort of calculate Q, Q would be the products with their exponents from the coefficients divided by the reactants. The exact same identical setup that you do for K, you do for Q. The difference is maybe we're doing initial concentrations here, so we're not sure their equilibrium concentrations, and it will allow us to determine, if they are we are at equilibrium. The other nice thing about Q is it will tell you if you're at equilibrium, but it will also tell you which way you need to go to reach equilibrium if you happen not to be there. So it actually gives you two really big pieces of information in a sort of direct, straight up Q type problem. It will tell you those two things. A, are you at equilibrium? And if the answer to that is no, then B, it will tell you basically, do you need to go make more products to reach equilibrium? Do you need to make more reactants to reach equilibrium? It will give you that information. So what is sort of that information? Well, we can compare the Q to the K value. So typically in these problems, like a straight sort of Q problem, they will give you the K value and you would calculate the Q value. And if you calculate the Q value and it is greater than the KC value, that means that we are not at equilibrium. And in order to reach equilibrium, we actually need to make more reactants. So it would head to the left. If you calculate Q and it equals the KC value, that means that, congratulations, you are at equilibrium, which would be this situation here. This was the first situation. And if you calculate Q and it's less than the K value, that means, again, you are not at equilibrium. And in order to reach equilibrium, you need to go to the right and make more products, which is this situation here. So if you kind of set it up like this with Q on the left and K on the right, you could kind of, an easy way to remember sort of which way it needs to go to reach equilibrium is by going opposite of where it's pointing to. So what I mean by that is if you go, again, sort of set it up like this, it's pointing to the right, which means it needs to go the opposite way to reach equilibrium. This guy's pointing to the left. He needs to go the opposite way to reach equilibrium. Obviously, if you flip them around, then it's pointing in the correct direction. But most of the time, we kind of go Q on left and K on the right. But so if it's set up that way, you can kind of remember it in that direction. So Q comes up in really two areas in sort of equilibrium problems. One is basically what we're discussing now, which is kind of how I refer to it as just a straight, Q problem. Basically, it's a problem where simply they ask you, hey, are you at equilibrium under these conditions? And if not, which way do you need to go to reach equilibrium? We will also see Q sort of pop up in a situation later on when we're given the starting amounts of everybody and we're not really sure if we are sort of at equilibrium, and it might affect the way you would do a calculation. So we will see it pop up here in just a bit, a little later on in this chapter, in a different sort of context. Any questions on Q? So again, calculated identical to how you would calculate the equilibrium expression. All right, then why don't you try one here and see what you come up with. If we start a reaction with 0.249 moles of N2, 3.21 moles times 10 to the minus 2 moles of H2, and some NH3. The Kc in this case is 1.2. Determine, is the system at equilibrium? And if not, which way you have to proceed? So basically, you should calculate the Q. So take a minute or two and see what you come up with. So we want to figure out Q in this case. They did give us the Kc value, and we want to compare Q to the Kc value. Remember that Q, again, is basically calculated the exact same way as you would do K. So we're going to take our products, which is NH3. We would square it because of the coefficient that we got going on there. That would be divided by our N2 and our H2. And again, for our H2, we would cube it in this case because of the 3 that we see there. In order to obviously do that, since those brackets again mean basically concentration or molarity, We do need to figure out the molarity of everybody here, so we could do that relatively easy. The N2 would be the moles that was given to us, which is 0.249 moles. The volume here is 3.5 liters. So that would give us our moles per liter. And looks like maybe you get 0.0711 molar. We could do the same thing here for our H2. Moles being 6.42 times 10 to the minus 4 moles divided by our 3.50 liters. And looks like maybe here we get 0.00917 molar. And lastly, we could do that for our NH3. And our NH3 would be, looks like, where did you go there? I think I wrote that one backwards. I did. Sorry. I calculated it right, but I wrote the wrong number there. Sorry about that. Let me just fix that real quick. The H2 number should be right. I just kind of wrote the wrong one there. H2, which should be the 3.21 times 10 to the minus 2. There we go. And NH3 is 6.42 times 10 to the minus 4 moles divided by our 3.50 liters. And that would give us 0.000183 molar in this particular case. Any questions on how to calculate the molarity there? At this point, we would go into our Q expression and put our numbers in. So our NH3, let me grab the right number here. It is 0.000183. Again, we're going to square it. We're going to divide it by our N2, which is this guy right there. That's going to be 0.0711. And we're going to times it by our H2, which is 0.00917. Again, we need to cube it there. Doing all that good math there, looks like we square the top number, divide by the bottom. Looks like we end up with 0.611 as our Q value. Any questions on how to calculate the Q value there? Okay, so what that then means is we have a Q value. We have the K value given to us, which was 1.2. In comparing those two numbers, we see that the Q value is less than the K value. First off, what does that tell us? Well, it tells us that we are definitely not at equilibrium. And second, what that tells us, again, opposite the way it's pointing, we need to go to products to reach equilibrium. So we need to make more products to reach equilibrium. Any questions on any part of that there? So this is what I would sort of consider a kind of straight up Q type problem where you're really just trying to answer kind of those two questions. Are you at equilibrium? And again, if you're not at equilibrium, which way you need to go to reach equilibrium. Any questions on that? Okay. Clearly, you can only calculate Q if you have enough information to do so. So obviously, if you're not given information about everybody in the reaction, there's no way you could possibly calculate Q. So this is one application of Q. Again, what we're going to talk about next, we will come across another sort of application of Q as well. So keep that in mind as we come across it. So let's talk then about sort of the really important thing here and really the major sort of calculation that we do in this class. And that is essentially solving equilibrium constant problems. So a lot of times what happens in problems is we're sort of given, initial concentrations, and we need a way to figure out how to get to equilibrium concentrations. So the most common way, and what we do a lot in this class, is we use what are referred to as ice tables. Now, ice tables, stand for initial, change, and equilibrium. So I run out of room there, but you get the idea. Equilibrium. Now, you may actually be familiar with ice tables, and maybe it depends on who you had for 1A, maybe our Chem 50, our first semester. And sometimes people will use ice tables for really limiting reagent type problems in stoichiometry. So it's a very common place to use. Sometimes we'll use ice tables, and it's very similar if you did that previously. A little bit different in sort of how we solve them, but kind of the same idea. If you didn't use sort of ice tables for stoichiometry and limiting reagents, that's okay. We're going to talk about obviously how to do that right now. But it's what we use here. And what that means is we need to figure out the initial concentrations, which are usually given to you. We represent the change usually in these tables as X. And the idea here is we want really only one unknown, like a normal math problem. We don't want a lot of different unknowns to try to figure out. And then we will eventually be able to figure out where everybody is when they reach equilibrium. So for example, let's say we had this reaction here where we had A plus B goes to, say, 2C. Now, we could write an equilibrium expression for this, which would be K is equal to C squared divided by A and divided by B. And we'll just say for the sake of argument that this value was 5. Okay. Now, let's say initially we started out with 2 molar of this guy and 2 molar of this guy. And initially, in most cases, you probably could assume that you're going to start with 0 of the products. So in these sort of ice table problems, if they give you information about just the reactants, it is a safe assumption that you're starting with 0 products. And that's a very common sort of situation that occurs in this type of problems. They oftentimes will just give you those sort of reactants. So 0 for initial for our products. Okay, it's very common as well. Now we get to the change part. So because we really have no products initially, we would assume that, when we look at this sort of reaction, that the forward direction here really should be what is being kicked off, right? Since we have no products, we got to start making some products, right? So to do that, we're going to convert some reactants into products. What does that mean about our reactants? Well, we would expect that in that process, these guys should go down, right, in concentration. These guys should kind of go up in concentration, right, as we're starting to make those things. We represent that in the change part as X. So in this case, this would be minus X. Minus because it's a reactant, it is decreasing sort of with time here, and we would expect it to sort of be lowering its concentration. Same thing with our B. We need A and B to make the products here, so this would be minus X. Now, there's a little bit more to this minus X than what I'm just putting here, and there's actually something else going on. It doesn't change anything, but what goes on for our change part is this is really where we do everybody's favorite thing, the stoichiometry part, the mole to mole relationship in this equation. And the coefficient here is 1, which is why this is technically 1x. No, he puts 1x, they just put x. This coefficient here is 1, which is why this is 1x. But when we come to our product side here, we don't have a 1 as a coefficient. We have a 2. So you do need to take that coefficient into account when you do the change part, because really what that is doing is your mole to mole relationship for you. So it's very important to take that into account. Also to take into account the idea, as we just talked about, we are going to be making some products here. So this would be 2x, the 2 because of the coefficient. Again, the x is the change. And we would expect the products to be increasing, which is why we would have the plus sign here on the product side. Any questions on that? At this point, what we would do is carry everybody down. So this would be 2 minus x, 2 minus x, and 2x. Any questions on sort of the setup of the ice table here? Now, what do you do with this at this point? Well, this is where the math comes in. We basically need to solve for x at this point. So how do we solve for x? Well, we use our equilibrium expression here. So we take our equilibrium line and we would put it into our k expression. So up on top would be 2x. And again, remember, we do need to square it. On the bottom would be 2 minus x, which would be a, and 2 minus x, which would be b in this case, and that would equal 5. At this point, we got a math problem, right? We need to go 4x squared on top. We need to factor and all that good stuff out on the bottom. We need to sort of solve for x. A couple different ways you can solve for x, but one common way and sort of the most complicated way that we will probably come across in this class is like the quadratic formula, if you will. So if you remember, you have something like ax squared plus b y plus c there is equal to 0. So we get something like this, and basically a, b, and c. And what we would do is, in this case, is we would want to, excuse me, we would want to use our quadratic formula, which is minus b plus or minus the square root of b squared minus 4ac divided by 2a. So in this particular case, when you use this, because it's plus or minus, you might be familiar with this, that you get basically two answers, and basically one will not make sense. Will not make sense there. And you'll obviously be able to find the x. Once you do find the x, that x would be all the x values here in our equilibrium line. That will allow you to figure out the equilibrium concentrations of everybody. Any questions sort of on that approach there? All right, so let us actually take a look at one here, and we'll do this one together to see how it all works out. And we'll do one to make sure the numbers work out rather than the one I just made up there. So let's take a look. We have this reaction here. Equilibrium constant is 7. We're starting with 0.663 molar of Br2. What is the equilibrium concentrations of everybody? So again, we could start with our equilibrium expression, which would be our products divided by our reactants. And again, this equals 7. So we would start with our ice table in this case. Initially, again, we are only given our reactant, which is 0.663. It is safe to assume that this is going to be 0. Because we don't have any products, we could also, again, safely assume that this reaction is probably heading in this direction, which means the reactant side would be negatives. The product side would be positives. So this would be negative x. Again, there's 1 for the coefficient here. This has a coefficient of 2, so this would be plus 2x. Again, that's a product, so we also should think it's increasing. That's why we have the plus there. That means when we reach equilibrium, 0.663 minus x and 2x. First off, any questions on the ice table, where any of that comes from or anything like that? Okay, so at this point, what we want to do is basically solve for x. So to do that, we're going to basically put everything into our equilibrium expression. And if we do that, the k would equal our products, which in this case would be 2x squared. Again, remember, you do need to square it because of the coefficient as well, divided by 0.663 minus x. and that is going to equal 7 in this particular case. At this point, what we want to do is we pretty much need to multiply the bottom to the other side. Also need to kind of square the top. So if we do that, we square the top, that gives us 4x squared. And if we multiply to the other side, we end up with 0.663 times 7 gives us 4.641 minus 7x. And again, we want to bring everybody to one side, and that would get us 4x squared plus 7x and minus 4.641 is equal to 0. And that is the form of the quadratic formula, our equation, which I think I butchered on the last slide. Let me rewrite that again. It didn't seem right. I put the y in there. Ax squared plus bx plus c is equal to 0. I think I had y equals mx plus b in my head, but that is the form of the quadratic formula there. And again, that does go with our quadratic little equation here. B squared minus 4ac divided by 2a. When we look at this, this guy here is a, this guy here is b, this guy here with the negative is c. Any questions on that there? So let us then put this into our formula here and see what we end up with. So x would equal minus b, which would be minus 7, plus or minus the square root of b squared, which would be 7 squared, minus 4 times a, which is 4, times c, which is minus 4.641, all divided by 2 times a, which is 4. So I'm going to kind of clean up some stuff here. We'll go with minus 7 plus or minus. If we kind of do the square root part, we're going to take 7 squared. We're going to minus it by 4 times minus 4.641. Looks like inside the square root gets us something like 123.256, which is, we obviously take the square root of that, ends up with 11.10 at the top there, divided by 8. So again, because it is plus or minus, where you could do both, so doing the plus root, the minus 7 plus the 11.5, so minus 7 plus 11.10 divided by 8 gives us a x value of 0.513, or if we do the minus 7 minus 11.10 divided by 8 gives us minus 2.263. Any questions on that so far? Now, you will always get kind of two numbers out of the quadratic formula, maybe two positive numbers, maybe two negative numbers, maybe a positive negative number, may even be two negative numbers are the two positive numbers. So one of these numbers, though, will not make sense. So what do we mean by that? Well, when I go back, for example, into this equilibrium line, remember that's what the x represents, is all these x's that we see here. If I took this number here and went back in with it, that would give me 2 times minus 2.263. That's going to give me a negative 4 point something type number. And you cannot have a negative concentration. So that is clearly not going to be the right x value for this situation. So again, one of those values, when you use the quadratic formula, will give you a negative value when you put it back into the equilibrium line. And obviously that would not be the correct value. The correct value obviously would be this guy right there, which would be our 0.513, which means if we look at our equilibrium line from the table for our BR2 just rewriting it here, 0.663 minus x. And for our BR, we had at the equilibrium 2x. We've now determined that our x value is 0.513. Those would go back in, which means that the concentration of Br2 at equilibrium is 0.663 minus 0.513. That is going to get us 0.663 minus 0.513, 0.150 molar as our concentration for Br2 in this case. And what does that mean for our Br concentration? Well, our Br concentration is equal to 2 times x, which means that would be 2 times 0.513, and that would get us 1.026 molar as the concentration at equilibrium of our Br. Any questions on that particular one there? Are the steps. Now, why is this sort of good math? Well, since it is math, and there is a lot of places where you could kind of screw up, you could actually check yourself to see if you did okay. How could you check yourself? Well, you could kind of check your answer if you have time by simply knowing, well, I know that the K is equal to Br squared divided by Br2, and I have now just calculated the equilibrium concentrations. Well, if I'm like, what just happened there? 1.026 squared divided by 0.150. Happens when you have too many BRs that look the same. 7.01 here. And what I was trying to say is obviously if you put these numbers in the right spots there, you will end up with obviously an equilibrium constant that should match the one that was given in the problem, if you remember. So it was 7 in the problem. So here, obviously, with rounding, it should be fairly close to the equilibrium expression there, value that was given to you. So it's a good way to check yourself. If you should end up with, the same equilibrium constant value as you started with in the problem. So that's a really good way to check yourself by putting those numbers back into the expression. And again, you should pretty much hit a K value that matches the one in the problem. Any questions on how to kind of do an ice table, perform an ice table? Obviously, be careful about putting numbers back in and make sure you put them in the right spot. Any questions on any of that stuff here? All right, so I think we will wrap it up for lecture here right now for today.